In this section, we're working on finding largest and smallest function values and what that has to do with derivatives. There's quite a few definitions in this section, so be patient. We're going to start with absolute max and absolute min values. An absolute maximum value means that the function is larger at some point than it is at all other points on the entire domain. Okay. An absolute minimum means it's the smallest value that occurs. So for instance, let's draw a function here. I'm just making this one up. Okay. An absolute maximum value means that the function is larger at that point than it is at any other point. So let's call this point loosely. It's about 5 and 6.5. All right. The function at this point right here at x equals 5 is larger than any other value. So the absolute max value is 6.5 and it occurs at x equals 5. The absolute minimum value in this case is 1 and it occurs at the point x equals 1. So there are two things going on here. We want the absolute value of the absolute max and min value of the function. That means we're interested in the y value. Okay. What the function values are the y coordinate. We're also interested in where that occurs, right? So it can occur at more than one place. For instance, if you look at sine, we know that sine looks like periodic graph, etc. So here's 0, here's 2 pi, and it goes through another cycle, 4 pi, and so on. So the absolute maximum that sine ever hits is 1, and that occurs in multiple places. The absolute max of sine of x is 1 and occurs, let's see, at pi over 2. Let's see, this would be 4 pi over 2, 5 pi over 2, 9 pi over 2. So it's pi over 2 plus any multiple of 2 pi. The absolute minimum value is at 3 pi over 2, but that's not the only one. And it occurs at 3 pi over 2 plus any multiple of pi. Now this multiple here can be a negative multiple as well. So that's what an absolute max or min is. Right. When we talk about the absolute max or min, we're talking about the largest or smallest value that the function can take on its entire domain. Right. We also talk about what are called local maxima and minimum. I just paused for a moment there to fix the focusing issue. Local maxes and mins are points where the function is larger than any nearby points, but it isn't necessarily the largest value around. So a local maximum value of f, right, is f of c, and it's a local maximum if it's bigger than the surrounding function values. So right here we have a local maximum on this function. At this number, let's call this number c1. So f of c1 is the local maximum value. At c2, we have a local minimum value because it's the smallest guy around. Right. When we talk about x near c, what we mean is that there is some open interval in the domain of the function for which this is the local minimum, the smallest guy around. All right? And when we talk about a local maximum here, we mean that there is a local interval, an open interval, where f is the largest at that point that it's going to be anywhere on that interval. All right, here's another maximum, another minimum. So you can have lots of local minimum and maxima. All right. What doesn't happen is the local maxes and mins don't occur at endpoints. So for instance, y equals square root x. Right. This has an absolute minimum value of 0 at x equals 0. But we don't say that this is a local minimum because it occurs at an endpoint. Right? It's not the biggest guy around on some open interval containing that point. Right? There are no points over here that I can use, only points over here. So there's not an open interval, okay, that contains 0 for which this is the largest value on that interval. So to be safe, when we're talking about a closed interval, you can't have a local max or min at an endpoint. Now notice also something about this function. Square root x has no absolute maximum value. It just grows and grows forever on its domain. All right. Let's look at a kind of a pathological example here and see what's going on. So at each one of these points, each one of these labeled locations, let's say if that's an absolute max or an absolute min. Okay. Well, if we want to know where the absolute max is, we need to look for the smallest y value on the entire domain here, and that's going to occur at A. So A is the absolute minimum. It is not a local minimum, okay, because it occurs in an endpoint. And that's an endpoint of the whole domain. This is going to be a little different thing that's going to happen at B, as we're going to talk about in a second. Where's the absolute max value? The absolute max occurs at R. But at R, we do have a local max because there's an open interval containing R for which this value right here is the largest guy over that whole interval. So yes, it's a local max. Right, let's look at the other points. At B, well, at B the function value is right here. Now that's the largest guy in some interval containing B. So at B we have a local max, but no absolute max. What about C? Right. At C, the function value is right here. It's not larger than the neighboring points, because right here there are larger points. It's not smaller than all the neighboring points, so we don't have a local max, and we certainly don't have an absolute max there. At D, there's an open interval containing D for which the function value at D is the smallest guy around. Right? So we have a local min there. It's not an absolute min because I have a smaller value over here at A. What about S? S is neither a local min nor an absolute min. It's not a local min. It's the smallest guy nearby, but it's not the smallest guy in an open interval containing S. Right? Because it occurs at an endpoint of the domain, right, it can't be a local max or a min. And it's also not an absolute max or an absolute min because there are larger and smaller function values. Right. We already looked at sign a little bit. I just want to revisit it a second here. This is the absolute max. This is the absolute max. There's another absolute max out here, and so on. Every one of these absolute maxima also corresponds to a local max. So we have an absolute max and a local max of 1. That's the maximum value. Whenever x is equal to pi over 2 plus any multiple of pi. That's the periodicity. We have an absolute min and a local min of -1 at the bottom of the unit circle, 3 pi over 2. But every time we go around the unit circle again, it happens again, so plus any multiple of 2 pi. So absolute max and absolute min can also be local maxes and mins, and vice versa. Let's look at a parabola here. Let's say y equals 1 minus x squared. That looks like this. Opens downward, has a y-intercept at 1, x. So y equals 1 is a local and absolute max, and it occurs at x equals 0. So right here, there's no absolute min, and there's no local min. This function keeps decreasing forever. Square root function, we saw this one on another page, but just to reiterate. The absolute minimum value occurs right here at the origin. So the absolute min value is y equals 0, and that occurs at x equals 0. And there's no absolute max. It grows forever. And there are no local minima. No local mins or local max. Right. You can't have a local extreme point at an endpoint. Cube function's kind of funny. It doesn't have a local max. It doesn't have anything. Here's what I mean by the cube function. Y equals x cubed. Okay. This point at the origin is a little peculiar. It looks like it's going to be a low spot, but then we go lower. Looks like it's going to be a high spot, but then we go higher. Right. So this has no maxes of any kind and no mins of any kind. Cube function is an important example. We're going to come back to it again later. Right. Because of something that happens here at the origin. We've got a horizontal tangent line here, yet this is not a max or a min of any kind. Likewise, absolute value is going to provide it as an important example for us. The absolute value function looks like a v. Seen that a few times. The absolute min and a local min, value of 0 at x equals 0, and there's no local or absolute max. Now what's peculiar about this function is we have this minima here, and it occurs at a point where we don't have a derivative. So some functions have absolute extrema, some don't. However, if we have a function which is continuous, and it's got to be continuous on a closed interval, then we can, because of continuity, this function has to hit a largest value and has to hit a smallest value. Compare this to the intermediate value theorem, which says if we start at one point and end at another value, we have to hit every value in between. Continuity buys us quite a lot. Okay, so let's look at a particular function here. Find the absolute max and min of f of x equals x squared. This one we can do pretty easily because we understand x squared pretty well. At -1, we're at a height of 1. And by the time we get over to 2 here, we're going to be a height of 4. This is the graph of the function x squared. It's a continuous function, and we're working on the closed interval from -1 to 2. So the absolute min, there is one, and it occurs right here. minimum value of y equals 0 at x equals 0, and the absolute max value is 4 at x equals 2. But it's essential here that we have both continuous and we have a closed interval. If your function isn't continuous, all kinds of crazy things can happen. Right, what if I considered the function y equals 1 over x minus 1 squared? That looks like this. It's got a vertical asymptote at x equals 1. Oh, you can't even see it. My apologies. So we're looking at this function y equals 1 over x minus 1 squared. Right. Its shape is basically this. It's got a vertical asymptote at x equals 1. On both sides we're going to plus infinity because the denominator here is always positive. So it doesn't have an absolute max. It has no absolute min. If I cut it off here, let's say I go from 0 to 2, right, then the absolute minimum value is the same. It occurs here and here. But it doesn't have an absolute max. And why doesn't it? Well, we're not continuous on the interval from 0 to 2. So the function continues to grow and grow and grow. Likewise, if you're working on an interval that isn't closed, let's look at, say, y equals the natural log of x. Okay, this is x equals 1 here. And now I'm going to, if I work on the interval, say, from 0 to 2, I can close it there, but I can't close it at 0 because natural log of 0 is undefined. So we have an absolute max there. The natural log of 2 would be the absolute maximum value. But there's no absolute minimum value because of this. We've got a vertical asymptote here. As x goes to 0 from the right, natural log of x goes to minus infinity. So we need both a continuous function and we have to have a closed interval. If we have that, then we're guaranteed to have an absolute max and min. If we don't have that, then all bets are off. What about local maxes and mins? Okay. If we have a continuous function on a closed interval, we're guaranteed to have an absolute max and an absolute min. Let's look at conditions where we might get a local max or a min. We're going to approach this a little differently. If we have a local max or min, let's see what happens. If we have a local max or min and we have a derivative, having a derivative means that we've got a tangent line. Well, the only way to have a local minimum here and have a tangent line is to have a horizontal tangent line. Same idea with a max. Right, if I'm going to be at a peak and have a derivative, right, then I have to have the derivative 0. So we have a theorem called Fermat's theorem, which says if f has a local max or a min, and if there's a derivative, then that derivative must be 0. Okay. What if you have a local max or a min and you don't have a derivative? Then what's going on? I can have a local max or a min, but right, I could have a situation with a local minimum like absolute value, so there's no derivative there, but we have a local minimum. Here's a local minimum. Right. So this function, this graph here, has a local minimum value at c. But it can also be the case that if I don't have a derivative, I don't have a local max or a min. For instance, if I had a corner that was shaped like that, no derivative, no tangent line there, but that's neither a local max nor a min. Or maybe I have a discontinuity. Does that do it? I guess we don't have a local max there because we don't have a value right at that point. We don't have a local min, so we failed to have a derivative here. So we're going to look at these kinds of points. Points where the derivative is 0, or points where the derivative fails to exist. And we give those points a special name. We call those critical numbers. A critical number is a place where there might be a local max or min. Okay. A critical number of a function is a number c where the function makes sense, it's in the domain, where either the derivative is 0 or the derivative does not exist. Okay. If you have a critical number, there may be, doesn't have to be, but there may be a max or a min there. Right. Absolute value, okay. Here we have a critical number at x equals 0 because the derivative fails to exist here. Right. And that is a local minimum as well as an absolute minimum. If I take your everyday basic parabola, so f prime of 0 does not exist here. If we look at f of x equals x squared, right, at 0 we have a horizontal tangent line. We also have a local minimum value and an absolute min value of 0 at x equals 0. Let's give an example where we have a critical number and yet it's not a max or a min at all. This is really important. Just because the derivative is 0 or just because the derivative doesn't exist, that doesn't guarantee you've got a max or a min. It just says that's a place that we might have one. Here's f of x equals x cubed. The derivative is 3x squared, and at 0 the derivative is of course 0. So right here at the origin I have a horizontal tangent line, but that's not a max or a min of any kind. So this is something you got to watch out for. Right. Just because you're at a place where the derivative is 0 or because the derivative fails to exist there does not necessarily mean that you have a max or a min. But if you turn it around, okay, if you turn it around, then if you do have a max or a min, then that location has to be a critical number. Right, if I have a max, say that kind, then I've got a critical number there because the derivative is 0. If I have a max with a corner, say, I've got a critical number there because the derivative fails to exist. If I have a max at some kind of a discontinuity, right, that's a critical number because the derivative fails to exist. Okay, so this is really important. If you've got a local max or a min at a certain x location, call it c, then we're guaranteed that that c is a critical number. But if c is a critical number of f, there might be a max or a min. So this means that critical numbers are the places to look for max and mins. So we're going to look for places where the derivative is 0 or the derivative does not exist. Right. But just because we have a critical number, there may or may not be one there. Right. A very important example to keep in mind is that cube function. It's a counterexample for many things. That means it shows certain things are false. Right. The derivative is 0, but I don't have a max or a min there. So one of the things we're going to be very interested in as we go forward here is finding these absolute max values and these absolute minimum values for a variety of different functions. If we have a function which is continuous on a closed interval, then we have a method called the closed interval method, which is a technique that always works, 3 steps, and is guaranteed to find for us the absolute max and min values. All right. What we're going to do is first locate all the critical values. We're going to note what the endpoints are. We're going to evaluate the function at those critical values and at the endpoints. And then the largest value we found is the absolute max, and the smallest value we found is the absolute min. Okay, I organize my thinking a little bit differently than the order of these three steps, but the idea is the same. First, what I'm going to do is find critical numbers. That means I need to figure out where the derivative either fails to exist or is zero. Well, polynomials have derivatives everywhere, so we're not going to have any critical numbers where this derivative fails to exist, but there could be some places where the derivative is zero. So I take the derivative, set it equal to 0, divide both sides by 6, and I get x is plus or minus 3. Okay. So on the closed interval from 0 to 4, I only need to consider x equals 3. I don't need to look at minus 3. And now what I'm going to do, this is where I say my organization is a little bit different. Same idea though. I'm going to make a list of all the critical numbers. I don't have to put minus 3 in there, but I need all the critical numbers that fall inside my interval and the endpoints. And at each one of those values, I'm going to evaluate my function. So when I plug 0 in, I get 5. When I plug in 3, I could just do it, but I pre-did this. I'm plugging back into the original function, not into the derivative. Here I get 113. And when I plug in 4, we get 93. So the largest of these values is the absolute max. So the absolute max of f is 113 and occurs at x equals 3. The absolute min is 5 and it occurs at x equals 0. So if you've got a function which you know to be continuous, things like polynomials and trig functions as long as you stay in the domain, rational functions as long as you're on the domain, if you know it's continuous on the closed interval, then it's guaranteed to have an absolute max and an absolute min. And if you follow this procedure, you find all the critical numbers that are inside the interval, you check the function values at the critical numbers and also at the ends of the interval, then you're guaranteed that in that list of values you'll have the absolute max and the absolute min. Okay, it'd be a good idea to organize your evaluations into a table like this so you can see that you've gotten them all and you could quickly communicate that you found all the points. Right, let's do one more example here. This one's a little hard. This is supposed to be the cube root of t. Got cut off there. Again, I'm going to find the critical numbers that are inside the range 0 to 8. Here I need a product rule. So I'm going to leave the first alone, differentiate the second. Plus take the derivative of the first, and leave the second alone. Right, this is where some of that simplification helps. I'm going to factor out some powers of t since these are on both sides of the plus sign that came from the product rule. And I'm going to factor out t to the 2/3. T to the minus 2/3 rather. So that means I need, when I factor out minus 2/3 from 1/3, I'm left with t to the first power. Notice if you multiply these back together, you'll get t to the 1/3. I still have the minus 1 there. Plus 1/3 times 8 minus t, because we factored out completely the t to the minus 2/3. So here I get minus t plus 8/3 minus t over 3. Hard part here is getting the derivative and getting it simplified to the point where you can work with it. This is not the only way to simplify it, but it is a way to do it. Now you could of course factor out a third here and maybe a 2 and so on, but that's not really important. What is important is that I get this thing into some kind of a factored form. Factoring out constants generally doesn't matter. where I can easily see where the derivative is 0 and where it's undefined. I got to find those critical numbers, places where the derivative is 0 or undefined. I can clearly see here, right, that the derivative is undefined at t equals 0. And the derivative is going to be 0 where the numerator is 0 here, right? Which I can inspect and see that it's at t equals 2, or you could set up the algebra. So at t equals 2, we have f prime of 2 equals 0. Right. Now I need to make a list. All my critical numbers are inside the range 0 to 8, and also the endpoints 0 and 8. So 0 is both a critical number. It's not inside the range, but it's also an endpoint, so we're going to check there anyway. When I plug in 0, I of course get 0 here. When we plug in 2, we get the cube root of 2 times 8 minus 2 is 6. When I plug in 8, I get the cube root of 8 times 8 minus 8, which is 0 because of the 8 minus 8. So the absolute min value is 0, and that occurs at t equals 0 and t equals 8. This is one of those that occurs in more than one location. The absolute max, I don't know what this number is exactly, but it doesn't matter. It's the only possible location where I could have an absolute max, right? Because it's the only other critical point. So the absolute max is 6 times the cube root of 2, and that occurs at t equals 2.